Good afternoon and welcome to Computer Science 311. Today we're going to be talking about hash tables. And you will find that hash tables are in your book. This is in chapter 11. And we'll be following what's in the book fairly closely. First of all, I think before we talk about hash tables specifically, I want to talk about what I would call the idealized data structure. So I want you to think about all of the data structures that we've looked at so far. We've looked at linked lists. We've looked at ordered arrays. We've looked at binary search trees, etc., etc. And there are a bunch of things that are common to all of these things. First of all, we would insert objects. We would search for objects. We would delete objects. We'd print them, etc., etc. And what we did in all of these things is we did some big O analysis of these things. So for example, to insert in a binary search tree, the complexity of that was typically log n. Likewise, binary search tree to search for something, the complexity of that would be log n. Remember, in both of these cases, these were if the tree was balanced. If the tree was imbalanced, these things could actually degenerate into order n complexity. If we had an ordered array, insertion in the worst case could be of order n, searching could be of order n. Linked lists, it depended upon whether these were ordered linked lists or if they weren't ordered linked lists. But again, we keep seeing numbers like this, order n, order log n. And computer scientists sit around and they go, well, can we do any better than these numbers? And they go, wouldn't it be nice, to quote the Beach Boys, wouldn't it be nice if we could do insertion and we could also do search in constant time? Big O of n is equal to just a constant. Wouldn't that be remarkable? That would be a whole lot better than these guys right over here. And basically what a hash table is a hash table is sort of an attempt at coming up with a data structure that can obey this time complexity here. Now, there's no free lunch in doing this. You gain a few things and you're going to lose a few things. Now, what you gain is that insertion and search can be done in constant time. And the question is what do you lose? And you do lose some stuff. Well, some people would claim you might lose the ability to delete. Although some would argue with that, and I'm going to put a question mark there because actually you really don't lose it. It just looks a little different. The other thing you lose is you lose the ability to list elements in order. In other words, in binary search tree, we learned that if we did an in-order traversal, we could see the things come out in alphabetical or numeric order. Similarly, the whole idea of an ordered array is the idea that the array is already ordered. So you can do binaries, you can do on an ordered array, actually if it's ordered, this is a mistake over here, this should be log n. How nice to work with a tablet. I can just stick that in there. But again, you can list things out in order. We're going to lose that ability here in hash tables, but we're going to see that that really doesn't cost us too much. The idea is that you're going to use hash tables for very specific types of applications, and we're going to learn about those in a second. So let's go to a new slide. So the idea here is that maybe we have some complex record And maybe over here there's a name. And maybe over here there's a GPA. Maybe over here there's an address. You get the idea. There are a bunch of fields here. And what we're going to do is we're going to pick a certain field. I'm going to come over here and pick name. And we're going to call that the key field. Okay? And the idea here is that I want you to imagine that we have a bunch of different records. So maybe we have David. And David has a GPA of 3.9. And I don't know David's address. I don't particularly care. And then maybe we have Bob, and maybe he's got a 3.8. And again, he's got some address over here. And then maybe we have Edward, 3.2, like that. We've got Al. Al's a very smart individual, like that. And then maybe we have someone named Cade, like that, 3.9. And it goes like that. And what we want to do is, so we see here that we have 5 names. And what I'd like to do is I would like to create a table. So a table looks very much like an array. And we can imagine that the table might be broken up into these pieces like this. And over here is the key, the name. And over here is the GPA. And here's other stuff here. And the idea is that we can even imagine the following, that the table is exactly the right size. So we've got a table over here with 5 elements. Okay. Now the whole idea of a hash table is we have something called a hash function. Okay, and we're going to call the hash function f. And basically what the hash function has to do is it has to take a key value and it's going to map it. Well, remember, this is 0, 1, 2, 3, 4. It's going to map it somehow to the set 0, 1, 2, 3, 4. Now, a couple of other things that we can say about this function f. F should be 1-to-1. I'm hoping you folks know that expression. It should be a 1-to-1 function. And it should also be, f should be an onto function. Okay, so if you don't know what that means, 1-to-1. 1-to-1 means if f of a equals f of b, then a equals b. That's another way of saying that we don't want 2 of these things to get mapped to the same number. In other words, if it turned out f of David and f of Edward both went to the number 2, then that would not be a 1-to-1 function. Okay? Onto means that for any one of these values that I see here from 0 to 4, I can pick any one of them, and there's got to be some value that maps onto it. So basically the way to think about this, I'm going to come over here and I'm going to say I've got key 1, I've got key 2, I've got key 3, I've got key 4, and I've got key 5, and I've got this table over here, 0, 1, 2, 3, 4. And what happens is these I'm going to draw a 1-to-1 function here now. See, that's 1 to 1 and onto. If I pick any one of these numbers here, if I pick 3, I can see that there is something that got mapped to 3. Okay? Likewise, I can see that no 2 of these values over here actually went to the same one over here. Okay, so I think that you can see the idea here. So this is what f does. So we, for example, in this thing here, we would say that f of key 1 is equal to 2. And we would say that f of key 2 is equal to, and it looks like it went 3. So the idea here of hashing is that we want this f function, f should be fast. Okay, it's something that the calculation is very fast and it gets us right to where we want to go. The other thing that we can see is that if I ever wanted to search, I just apply the f function. It gets me over to the proper place in the table and I can read the whole thing off. Okay, so the idea here is that you can see here that insertion as well as searching is just in order of this function right here, f. Okay, and it's something that we make very fast. It's something that can be calculated in a very fast time. That's the idea of hashing right there. But you can see that there are a couple of issues here. There really is no way to print the names off in order. I could certainly start over here and just print the things out here this way, but I have no idea if these things are going to print out in alphabetical order. It all depends on what the value f is. Okay, so that's the idea of hashing. So we could come over here and we could consider a couple of ideas here. So first of all, you may remember, and I'm just referring to my keys now. We had Al. I'm trying to remember the people we had here. We had David, and then we had Cade, and then maybe we had Bob, and then we had Edward. And one example I could give of a function is I would come over here and I would say, if I'm going to calculate f of Al, I'm going to say, let's look at the first letter. And let's use the mapping that A would go to 0, and B would go to 1, and C would go to 2. And we're going to come over here and we're going to see that f of A is 0. So we're going to send this to a 0. And then f of this, I come over here and I look at the D. Well, clearly that would just go to a 3. And f of C would go to a 2. And f of B would go to 1. And f of Edward would go to 4. And we see we have a very nice property here. We see that, first of all, it is a 1-to-1 mapping. And the other thing we see is that it is onto the set 0, 1, 2, 3, 4. Now, admittedly, this was a very contrived example here, and the names, okay, happen to be picked because of this nice property here. I want you to notice another function I could do is I could just say that f of the string, if I knew how to spell string, how about if I were to let it be string.length minus 1? And again, you would see that you're going to get the same mapping over here. And again, no mistake, it's the way I chose it. But now there are a couple of things over here. You can see there's a problem. First of all, what if the names I had were Al, Adam, Adrian, Bob, and Bill? The problem we have now is that these three over here all appear that they're going to map to 0, and these two over here all appear that they map to 1. So first of all, when this happens over here, we have what's called a collision. So there's a collision of these three, and over here we also have a collision. And the question is what do you do? And the answer to that is a little bit complicated. So let's consider a couple of things here. We want to implement hashing. And we have a bunch of keys. So this key 1, this key 2, key 3, all the way up to some key K. Now, normally there's going to be some table over here that we're trying to hash these things into. And we're not going to be so lucky as we were in the examples that I just gave you. So one thing that we got to do, okay, remember the whole idea here is these things called collisions are problems. And we would like to eliminate them completely. We're not going to be able to do that. But we would like to make them less likely. So one way to make them less likely is if I come over here and I have this table, if there are k of these keys, I'm going to come over here and I'm going to have a table with n-1 entries. And I'm going to make sure that k is less than, I'm going to draw 2 of these, okay? That we certainly want to have the case that k is a lot less than n. Okay, the idea here being that if this thing is big, there's going to be less likelihood of a collision. Okay, now this brings up a very, very interesting problem before we proceed any further, and I'm sure that you folks have probably seen this. There is the so-called birthday problem. And the birthday problem goes something like this. Let me just... All right, it's not the birthday problem. Birthday problem goes like this. There are 365 days in a year. So imagine a very big table like this. 0, 1, 2, 3, all the way up to 364. And we have a bunch of people over here. I'm going to say P1, P2, P3, P4, all the way up to some PK. And the question that we have is what is the probability that all of these K people have different birthdays? And when I'm saying birthdays now, I'm just referring to month and day. And in fact, what I'm actually referring to is the day number of the year. Okay, so if your birthday is February 2nd, well, that actually would correspond to, I have to think about this, 30 days have September, April, June, and November. So January has 31 days. So February the 2nd would actually correspond to 33. Everybody get it? So what I'm asking here is what is the probability that these K people are all going to have different birthdays? And that's another way of saying that I want to come up with a function, okay, that just assures that it's not going to be onto, because I'm going to assume that K is much smaller than 364. But what it is going to be is I do want it to be 1-to-1. I don't want people to have the same birthday. So here's a way to think about it. If I just have two people, P1 and P2, what is the probability that they have different birthdays? Well, the first person can have a birthday on any of 365 days. And then the second person just has to pick 364 out of those 365. So this would be the probability that two people have different birthdays. If I had three people, okay, the probability that all three of these people have different birthdays would just be, well, here's the probability that two people have different birthdays, and now the third person has to pick from the remaining days. That's going to be 363 over 365. And if I had four people, then the probability is going to be this times 362 over 365. So remember, this is giving us the probability here that four people have different birthdays throughout the year. So here's the interesting question. How many people do I need to have before this number here gets less than a half? And the answer is somewhere around 23 people. Which is really a very surprising result. In other words, I think that our 311 class has 30 students in it. And what the mathematics tells us then is that the probability is actually pretty high, it's certainly greater than a half, that there are two people that have exactly the same birthday. So that's the problem again that you run into in hashing. Where is my last one? I don't know where it is, but we'll just put up another one here. Oh, right over here. So the idea is, as you can see over here, when n was 365 and k is about 25, the mathematics tells us that even if these things are uniformly distributed, the probability is already greater than a half that there is going to be a collision. Okay, so the question is, what can we do about collisions? Okay, so one thing we can do is we'll say is choose a good hash function. So how do we choose a good hash function? Well, let's think about a couple of possibilities. So let's get another thing up here. So let's think about this a little bit. So let's consider a string, I don't know, something like ABC. And I want to think about what should this map to? Okay, well, first of all, one of the things we could do is we could certainly say, well, I'm going to let A map to 0, and I'm going to let B map to 1, and C map to 2. I'll take this all the way down to Z would map to 25. And I'm going to say, well, let f of ABC just equal the value of these individual letters and sum them up. So that would be a 0 plus a 1 plus a 2 is equal to 3. Okay, not a bad idea. What about if I were to say, well, then what's f of C? F of C is 2, yeah. What would f of BC be? Well, that would be 1 plus 2 is equal to 3. So we can see that these two are actually the same. And in fact, if I were to come over here and I were to say, what is f of C be? That would equal 1 plus 2, and that's equal to 3. And in fact, if I came over here and I were to say, what is f of A, C, B, A, whoops, and stop right there. It's getting a little carried away. Well, that's equal to 0 plus 2 plus 1 plus 0 plus 0 is equal to 3. And that's also the same. So I can see that there are a lot of collisions here. Just here, I've created a collision with this one, and with this one, and with this one right over here. So I don't think that this is necessarily a good idea. What would be nice is can we get strings to map to unique numbers? And the answer is sure. Here's what I want to do. First of all, I want to change this mapping a little bit. Okay? Because this 0 is going to be problematic. And what I'm going to do is I'm going to say I don't want that to be 0. I want it to be a 1. I want this B to be a 2. I want this C to be a 3. I want the Z to go all the way up to 26. So instead of going from 0 to 25, I want to go from 1 to 26. And what I want to do is I want to think about our friends, the integers, and I want you to remember if I write down something like this if I write down 239, remember that's 9 times 10 to the 0. And this over here is 3 times 10 to the first. And this over here is 2 times 10 squared. And what I want to do is I want to do the same thing with strings, A, B, C. But now what I want to do is I want these letters to be in powers of 26. So C is 3. I want this to be 3 times 26 to the 0. And I want this one to be, B would be a 2. I want that to be 2 times 26 to the first. And A is a 1. I want that to be a 1 times 26 squared. Okay? And you can see that then what I want to do is I want to add these numbers up. And what that's going to do is that's going to make f of ABC very different from f of CAB and f of CBA. These are now going to be different numbers, okay? This would almost be like looking at 239, and this would be looking at 923, and this one over here would be looking at 932. These are absolutely different numbers, even though they're the same symbols. So when I use this mapping over here, okay, I am now mapping these things to unique numbers over here. Now, what's a little bit bothersome is what if there was a z in there? So if there was a z in there, I would be having 26 times 26 to some power over here, which is in essence raising this up to even a higher power. Some would argue that that actually means we should take these things back to our original numbers where it was 0 through 25. That's not going to be an issue right here for the moment. So now the question is now I've got what I think is a nice hash function, but now where are they going to get mapped to? So the idea here would be something like the following, that I have these various strings, A, B, C, and I have cat, and I have dog, and I have mouse. And what I'm going to do is I'm going to have my table over here. Zero, 1, 2, 3, all the way up to some n-1. And we're going to assume over here that there are k elements to insert. And basically what I want to do is I want to do over here is I want to say pick n such that n is much bigger than k and n is a prime number. Okay? And the reason why we want this to be a prime number is because when we come over here and we calculate, say, f of ABC, well, remember, that's going to be 1 times 26 squared plus 2 times 26 to the first plus 3 times 26, 0. And what I'm going to do is I'm going to divide this thing by p, or I'm going to look at the remainder mod p. And when I look at it, the remainder mod p, that's going to send it to some place in this table over here. Okay? So for example, I don't know, and again, this is more art than science. If I knew that I was going to be hashing 20 elements, okay, I might pick p. I don't know, I'd have to think about this. P, let p be 119. Is p a prime there? I don't know. Do you know how to check for primality? Well, 9, 10, 11, I know 3 doesn't go into that. I know 5 doesn't go into that. Does 7 go into that? and unfortunately 7 does go into that. So 119 is not a prime. Is 121 a prime? So 3 doesn't go into that, 5 doesn't go into that, 7 doesn't go into that. 11 times 11 is 121. That doesn't work. What about 123? 3 divides 123. So you can see we can spend a lot of time doing this. 127, 7, 8, 9, 10. 3 doesn't go into that, 5 doesn't go into that, 7 doesn't go into that, 11 doesn't go into that. So that is a prime. So if I were going to hash 20 elements, I might pick P to be 127, and I would be doing these calculations right over here. I want to discuss a little bit what I just did. How did I find that prime number? Let me find my cursor then. I said that 127 is prime. How do I know? Okay, there's a very famous theorem in number theory. And it says the following: if n is composite, remember what composite means. Composite means it's not prime. If n is composite, then n is divisible by some prime less than or equal to the square root of n. Okay, otherwise n is prime. So let's see what I just did here. I claimed that 127 is prime. Let's see if I'm correct about that. So first of all, there are a couple of things let's look at small primes. We know that 2 is a prime. We know that 3 is a prime. We know that 5 is a prime. 7 is a prime. 9 isn't. 11 is a prime. 13 is a prime. And what I want you to note, I want to square these numbers. If I square this, I get 4. If I square this, I get 9. If I square this, I get 25. If I square this, I get 49. 11 squared is 121. 13 squared is 169. Now I'm checking to see if 127 is a prime. So what that is telling me is I just need to come over here and I need to see if any one of these prime numbers divides 127. Well, 2 doesn't divide 127. 127 is an odd number. Does 3 divide 127? Well, there's a trick here. If I add up these digits, I get 7, 8, 9, 10, and 3 doesn't divide 10, so 3 doesn't divide 127. We can see that 5 doesn't divide 127, because if 5 divides a number, that number either ends in a 5 or a 0. Does 7 divide 127? I don't know. 7 goes into 127, that's 1, 7, that's 57, that's 8, that's 56, and there's a 1, so no, it doesn't. And then the question is does 11 divide 127? Well, we know that 11 squared is 121. 11 times 12 would be 133. So this doesn't divide it either. So all of the primes less than the square root of 127 do not divide it. Therefore, 127 is a prime number. And that is our bit of number theory for today. I hope you enjoyed it. Now back to hashing. Okay, let's pick up on what we were talking about, and I need some more writing room here. So let us imagine, let me find my cursor, there it is right there. So let's imagine that we've got Abe, and we've got, I don't know, cab, and maybe we have, I don't know, I'm just trying to keep the, let's say bad. I don't think anyone's named bad. But we want to come over there, and we have, let's suppose it's a very small table here. Zero, 1, 2, 3, 4, 5, 6, and that's p minus 1, so p is equal to 7. So A would go to 1 times 26 squared plus 2 times 26 to the first, plus, let's see, A, B, C, D, E is 5 plus 5, okay, times 26 to the 0. Cab would go to 0, 1, 2, 2 times 26 squared plus 1 times 26 to the first plus 2 times 26 to the 0. By the way, this would be mod 7. This would be mod 7. And this would go to, let's see, this should be a 3 here. 3, 1, 2. This would be 2 times 26 squared plus 1 times 26 to the first plus 4 times 26 to the 0. And again, that is going to be mod 7. And I would come over here, and I've got my Wolfram Alpha that's going to help me calculate these big numbers. And I'm going to come over here. Please be patient as I grab my keyboard. So over here, I have to go. My keyboard does not appear to be working. There we go. I'm going to go 1 times 26 to the second plus 2 times 26 to the first plus and 5 like that, and I'm going to go mod 7, and it tells me that the answer is 5. So that tells me that ABE, I'm switching a lot of things here, so please bear with me. That's going to go to 5. I come over here, so over here is where Abe would map to. So let's come over here and see where Cape would go to, and I've just got to change some of these numbers around. So that 1 is going to become a 3. And then over here, I'm going to get a 1. And over here, I'm going to say 2. Oh, and look at that. That also goes to 5. That's going to be great for our demonstration here about what to do in a collision. So this also went to 5. And what happens if I put bad in there? And I'm going to calculate this. I'm going to make that a 2. I'm going to make that a 1. And I'm going to add a 4. And that goes to 3. So that means that bad would go to here. Okay, but look at this. We had a collision. What to do? Okay, and what we have to talk about here are what are called resolution techniques. Or in other words, we have to talk about what's called collision resolution. Almost sounds like a negotiation. Collision resolution. Okay, and method number 1 is what's referred to as linear probing. So first of all, we use the word probing in hashing. Probing means we've gone into the table and we've done something. So in other words, what happened over here, when I calculated f of cab, I got 5, and it took me over to 5, and I saw that this thing was occupied. So what do? I start probing right after it. I keep adding 1 to it. So in other words, I look at f of key, mod p, and then I look at f of key plus 1, mod p, and then I look at f of key plus 2, mod p. So in other words, in this case here, if I have something that mapped over to here, then what I do is first I would check this one. And if that's also occupied, then I'd come over here and I would check this one. And if that's occupied, I'd keep coming over here and I'd check that one. Okay? So with this linear probing, it just means that I keep adding 1 to the previous one and see if that's available. So in this case over here, number 6 is available, and what I would do over here is I would come over here and I would put cab in here. Okay? Now, I'm going to come over here and I'm going to say, what are the problems with linear probing? And the answer is the following. The answer is you're going to get what are called clusters. In other words, suppose f of key 1 is equal to f of key 2 is equal to a whole bunch of keys that all go to the same place. So what's going to happen is you're going to get, here's where f of key went. And then what's going to happen if I have lots of keys that all map to here, well, then this will be occupied, and this will be occupied, and this will be occupied. And you can see what's happening is you're developing a cluster over here. So now what happens is if I have some other key that maps over to here, it's going to go, well, gee, that's occupied already, and it too is going to have to start doing linear probing. So that the problem you have is that if you have a bunch of keys that are all going to either be the same or real near each other, you're going to get, you might have a very big hash table like this, and you're going to get that things are going to cluster very closely together. And that's not good. Remember, the ideal situation is you would really like these things to be sort of evenly spread through the table. Okay? If they're evenly spread through the table, there's less likelihood of a collision. Okay? When they're all packed in close like this, okay, there's a much higher likelihood of a collision. And remember, once you start getting collisions, all of a sudden the behavior, the timing characteristics are no longer big O of n is equal to a constant. In fact, if you had that all of the keys all hashed to the same number, you're going to get that insertion time is now going to be of order n. I'd have to go through all of them to actually find one. Okay? So for that reason, linear probing is not really considered all that great. So what are the alternatives? Well, the next thing that we talk about is something that's called quadratic probing. And the idea of quadratic probing just says the following. If f of key is occupied, look at f of key plus 1 mod p, f of key plus 4 mod p, f of key plus 9 mod p. And basically you just want to look at f of key plus k squared mod p for k equals 1, 2, 3, 4, like that. Now, so what is this supposed to do for you? Well, the idea being, again, here's our hash table. So suppose we come over and we hash over to this spot right over here. Okay, so suppose that this is occupied. Okay, so then it says the next place that I would check is I would look at +1. So I would check this space. And if that's occupied, then what I would do is look at +4, +1, +2, +3, +4. So I would now check this one over here. And if that's occupied, I would go +5, +6, +7, +8, +9. I'd now check over here. So you can see where I'm going to put a question mark here, and I'll put a question mark here. And you can see that what we appear to be doing, okay, is we appear that now that when there is a collision, is we appear to be creating spaces between where we subsequently try. Okay, the idea being now, if something else is going to come along and it's going to hash right over to here, there's no collision, and we have lots of spaces here to leave for something to hash to, no problem. But in a way, we really haven't solved the problem, because if I have the case that f of key 1 is equal to f of key 2 is equal to f of key 3, if that in fact happens, you can see what's going to happen. I'm going to start to get clusters around these places right over here. In other words, all of these are not only going to get hashed to the same spot, but I'm going to start checking the same spots, for where I can resolve to put them. So whereas it's creating spaces, okay, between here where I could ultimately hash other values, if I'm unlucky and I have the case where a lot of keys actually hash to the same value, I'm still going to have the same problem, that there's going to be clusters created around these spots right over here. So the question is this better? And the answer is a little. Okay, so let's see if we can find a better solution to linear probing or to quadratic probing, and there is a better solution. And in fact, this is the solution that most people use. Let me just create some empty screens for me to use here, and I'll be with you in a moment. So the idea is the following. And let me get this on screen. There we go. I can get this one out of the way. Get this one out of the way. Get this one out of the way. Okay. Thank you for bearing with me. Now we can talk about some stuff. Okay, so this is, I seem to have lost, there's my cursor, right over there. So the ultimate is what's called rehashing, which is another way of saying use a second hash function. To determine a step size. So the idea here is the following. We have what we've done to now when we had linear hashing. Okay, remember what happened or when we had linear resolution is as if you had f of key 2 was equal to f of key 1. Okay, so what would happen is key 1 would go over here, f of key 2 would go over here, and we'd see that it was occupied. We just started skipping by 1. First we'd check over here, and if this was occupied, then we'd check here, and if that was occupied, we kept doing this. We kept stepping by 1. So that would be linear. And then we looked at quadratic, which said first we would go +1, then we would go +4, so that'd be 1, 2, 3, 4. We would come down to here. So I'm going to say +1, +4. We would go +9, basically plus k squared mod p. Okay, and that would be quadratic. And we said the problem with both of these is that if you had multiple keys that all, if we had f of key 1 is equal to f of key 2, which is equal to f of key 3, which was equal to f of key 4, not only are all of these going to hash to the same original spot, but when we go ahead and try to resolve where we're going to put them, they're still going to continue to bump into each other. If they're all using the same step size, they're going to keep bumping into each other. So the idea here of rehashing is to have a second hash function, and we'll call it g. Okay, and it's basically you want to pick g in such a way so that we want to say the following, that if f of key 1 is equal to f of key 2, what you would like is then g of key 1 doesn't equal g of key 2. And what we do is this becomes the step size. Okay? The step size meaning how far you jump each time when you have a collision. So let me give an example of how this would all work. So what I've got here is I want to assume the following, that I've got the following names. I've got Al, and I've got Abe, and I've got Cal, and I've got Dak. Yes, I know that's a funny name. And I've got Ed, and I've got Bab. And what I've decided here is that my prime is going to be 11. So for example, when I come over here and I calculate this, remember what this is going to be, a is a 1, so that's going to be 1 times 26 to the first plus, and L, it turns out, is actually the number 11, so it's going to be 11 times 26 to the 0, and I'm going to compute this all to be mod 11. And I won't bore you by going back to wolfram.com to show you the calculations, but when I go ahead and calculate this, this turns out to be 1. And when I come over here and I do ABE, that is 1 times 26 squared plus the B is a 2, so that's 2 times 26 to the first plus E would be 5 times 26 to the 0, and I do that mod 11, mod 11, and that actually turns out to be 7, and I come over here and I do cal, so that is 3 times 26 squared plus 1 times 26 to the first plus 11 times 26 to the 0, and that turns out to be 9. And I come over here and I do DAC, and DAC is equal to 4 times 26 squared plus 1 times 26 to the first plus 3 times 26 to the 0. And again, this is mod 11. I'm getting a little sloppy here. Let me do this. So this was mod 11, and that's equal to 9. And this mod 11 is equal to 5. And I come over here and I look at ed, and ed would be equal to 5 times 26 to the first plus 4 times 26 to the 0, mod 11, and that is equal to 2. So first of all, when I come over here and I draw this, one, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, if I'm doing it mod 11, it only goes up to 10. So I don't need this. Okay, so the first thing that we see, if I come over here, here's Al. And 7 is Abe. And Cal is at 9. And I've got Dak at 5. That's Dak. And then I've got Ed at 2. Okay, now if I come over here and I calculate Bab, that is actually going to be 2 times 26 squared plus 1 times 26 to the first plus 2 times 26 to the 0. And when I do that mod 11, I am going to get a 5. So I've got a conflict right over there. So the question is how do I rehash this? Well, P was equal to 11. So the first thing you'd want to do is pick a prime Q less than P. Okay, and what I'm going to do here is I'm just going to say let Q equal 7. Okay, and then what you do over here is I am going to say let the step size equal Q minus, okay, and what I'm going to do over here is I'm going to calculate f of the string mod Q. Now let's think about what this means over here. First of all, you realize over here, f of the string mod Q, this over here is going to give me some number that's either 0, 1, 2, all the way up to Q minus 1. Okay? And then when I go Q minus this, what this is going to do is this is going to give me, if I go Q minus this, I'm going to get either Q minus 1, Q minus 2, down to 1. And that's my new step size right over there. So over here, I come over here and I calculate Bab again, but now what I'm going to do is I am going to calculate 2 to this 26 squared plus 1 times 26 to the first plus 2 times 26 to the 0. But now what I'm going to do is I'm going to calculate that mod 7. And when I calculated mod 7, okay, I come back here and I don't remember what I got here. I am going to get 1. Okay, and now according to this, what I'm going to do is I'm going to go my step size is equal to q minus f of string, so it's going to be 7 minus 1 is equal to 6. So what does that say to me? Well, it says I'm going to come over here, and now what I'm going to do is I want to put Bab in, but Bab is occupied. But DAC is occupied, so I'm now going to add 6. So I'm going to go plus 1, plus 2, plus 3, plus 4, plus 5. I'm going to wrap it around, and here I am at plus 6, and this spot is available. So I would come over here, and I would put Bab in here. And there I am. I'm done. On the other hand, let us suppose that this one was occupied as well. So then I'd have to count another 6. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. So if this was occupied, I would try to put it in over here. See, the whole key to this thing over here is that if f of key 1 is equal to f of key 2, what we're hoping is that g of key 1 doesn't equal g of key 2, which means we'll get different step sizes for them. Hence, we won't get a whole lot of this clustering that you got over with the linear probing and the quadratic probing. So that is the end of the lesson, and I would say the following. I will finish it up like this. Okay, read the chapter on hashing. Okay, specifically linear probing, quadratic probing, and rehashing. I will be assigning homework. And you must hand it in. It will be graded, and that will be indicated to you on the website. So I hope you have enjoyed the video. Tune in again soon.